aware that some people, maybe they were working and their computers crashed or whatnot a few times, depending, I guess, where you lived. But hopefully this extension lets everybody finish up and complete the first assignment. Again, it's on MML, and if you still haven't signed up for MML, I mean, you really have to do it now, basically, because I don't like to give or extend deadlines unless there is a good reason for it. So that's first announcement. The second announcement is our first quiz. In general, our quizzes are going to be I'll give you a little more instructions on that, but for exams and study guides, you will have to upload your work, as we mentioned on our first meeting. A little more information about the quiz. So it'll become available around midnight today. I think I'm going to finish up creating it after our lecture, and I'll start it basically at 12 a.m. today. So it'll open today at 12 a.m. And I will give you a 24-hour window to get it done. So 24 hours means that tomorrow by 11:59 p.m. it should already be submitted. So don't start it at midnight, obviously, right? Because you do need time to finish it. And that gives you a 24-hour window, which I think most people will find, an hour or 45 minutes. Or if you decide to take it twice, which I'm letting you do, and then maybe an hour and a half to get the quiz done. If for whatever reason that window absolutely doesn't work for you, email me or message me through Canvas, explain your situation, and I will consider shifting the window for the next quiz and for this quiz for you individually if somehow the 24-hour period from today till tomorrow night doesn't work out for you. A little more information is there is 45-minute timer for the quiz, and it'll probably be around 4 questions. I'm going to say 3 to 5 questions. So should be enough time, shouldn't be too bad. And that way, I'm also giving you 2 attempts. So 2 tries, 2 attempts for the quiz. So that way, if you took it the first time and you're going to see your score and you're not happy with your score, you can take it again, and hopefully you'll know where you messed up, but it will not tell you. So once you submitted the first time, it will not tell you that you got question number 2 and number 4 incorrect. It'll just tell you your overall grade, and it'll let you take it one more time. So 2 attempts. The question, where is it located? So it'll be in MML, and it will be in assignments section, but it is not open yet. So it opens today at midnight. And make sure that when you guys open your MML assignments, I mean, you don't have to start it right at midnight. You can just start it tomorrow morning or tomorrow evening, whenever time allows for it. Or if you want, you can do it after, tonight, late, who knows. So once you completed both of your attempts, then the better of the 2 is what's kept. And after the due date, which is again tomorrow midnight, after it's due, then you can go into your grades and you can see where and which questions you made mistakes on, but not until it's due, because I don't want people communicating with other people, basically. So once the due date has passed, then you can go back and check your results and see what questions you made mistakes on, and hopefully do some error analysis, things of that nature, and understand why you messed up. Because it's our first quiz, I will allow you to message me if you think that that I should look into your quiz and fix your grade a little bit, because let's say your work was correct, but due to some input error on your end, maybe some minor error on your end, maybe it counted it incorrectly, or maybe some questions you thought you simplified it correctly. So you can still message me and I might take a look at it, but usually I do that for exams. I'll look at all of your questions on the exams and kind of compare what you submitted versus what you should have submitted and give you partial points. On quizzes, I prefer that the computer just grades it. So because it's the first quiz and we're still perhaps getting used to the MML shell, the MML program, whatever platform, you can ask me to look over something if you're not happy with it. So yeah, the best grade out of 2. And the lessons that it's on, it's always going to be on whatever the homework was on. So in this case, last week homework, right? And that's always going to be the case for our quizzes. Whatever we do this week, I can quiz you next week on. Whatever we do next week, I can quiz you the following week, and so forth, right? So last week we did 1.1, 1.4, 2.1, 2.2. So those are the lessons that you should expect the quiz to cover, basically. Yeah. Any other questions regarding the quiz? Anything I need to clarify before we jump into our lectures? No, everybody's still. Yeah, go ahead.
So where do we check for the code for the NLA to access it?
So to access MML, make sure that you read your syllabus, right? Because this syllabus contains a ton of information, and if you were not present during the first day, that means you missed out on a bunch of information. So now you'd have to catch up, read the syllabus. The syllabus contains course ID, but MML is a paid program, so it's like $60 or $68 if you buy it through the bookstore for the access code. So you would need to have the course ID, which is in the syllabus, and then the access code, which you have to purchase. But make sure you get on top of that.
Oh, so I'm gonna have to personally purchase the access code?
Yeah, it is something that you're required to have for this class. It'll also give you access to the book and basically everything else that MML contains, the lessons, the videos, and everything else. What lessons will the quiz be exactly like the homework or close to? So basically, yes. I mean, it cannot be exactly, because the questions are always generated by a computer, so it'll be the same type of questions, right? I'll pick 3 to 5 of those questions that were on your homework, and that means that it is very similar, or if you want to say exactly like or close to the homework. Yeah, definitely. All right. So
Professor, my question is, since like you mentioned that the quiz will be open and by midnight tonight, that means can we actually do it on our own time, right?
Correct. For the quiz, yes, you can work on the quiz at your own time. I'm giving you a 24-hour window by when you have to complete it, and you can choose, when you want to get it done. So for the quiz, I allow for that, similar to the homework. For the homework, of course, you guys have like a week window. For the quiz, for now, 24 hours, but exams will be different. So this is a quiz separate from the exams, and we'll talk more about the exams when we get closer to the exam. All right. Anything else before we start on our lessons? Alrighty, then let's go ahead and start on 2.3. 2.3 is a nice lengthy lesson with a lot of different new concepts that you guys will need to kind of be introduced to. And later on in calculus, you will use a lot of them. For pre-calc, we will use some of them. I can't necessarily say that we will use all of these concepts from today's lesson, but at least you'll be introduced to them, and then then when you need to pick them up for calc, you'll hopefully remember them. So 2.3 is our next lesson. It is referred to as properties of functions. And we're going to consider various types of properties like odd, even, increasing, decreasing, local maximums, local minimums, so a whole lot of concepts. And we will start with odd versus even concept, odd and even functions. Just like we define integers to be odd or even, we can say an integer is even if it's divisible by 2 without a remainder. An integer is odd if it's not divisible by 2 without a remainder. But for functions, it's a bit more complicated. The definition for an even function is that, so even algebraically is you have to evaluate the function at negative x. Let's see, there's a question there. Last question for homework. I thought it's always due the next week. So previous week's homework was due today, but I extended it. So yeah, it's always due the next week. I'm not sure I followed your question exactly, but whatever is this week's homework is going to be due next week. Whatever was last week's homework was due this week. Yeah, so that doesn't change. So even, again, to check if a function is even, we plug in and evaluate that function at negative x. And if the result is equal to the original function, then we say that that was an even function. For odd, similar start, we evaluate the function at negative x, and if the result is negative f of x, after we have simplified it, then we say we have an odd function. So these are the algebraic definitions of odd versus even. So really easy examples are if we talk about f of x equals x squared, and we want to check if it's odd or even or neither, right? Because if it's neither odd nor even, then we say it's neither or neither, however you prefer to pronounce it. So to check, we would plug in f of negative x. Our function is input squared or x squared. Our input is negative x. Negative x squared would give us positive x squared. Again, if you need to show a little bit of scratch work as to why there is some properties of exponents, we know that negative x squared is simply negative 1 times x, both squared, and then we have a property that tells us each factor gets squared. We know that negative 1 to an even power is always 1. So that's how we would just get x squared from there if we need to show those steps. But now we can say, well, x squared is exactly the original function, right? That's what the original f of x was. So x squared is equal to the original function f of x. We were able to show that f of negative x is equal to f of x. Therefore, this function is said to be even, because that's what the definition tells us. And similar, if I look at a different function, let's call it g. Name of the function is not too important. Let's call this function g of x, and it will be x cubed, for example. Then we can show that this will be an odd function. Using a very similar approach, we would start by evaluating the function at negative x. So g evaluated at negative x, my function g is x cubed, so negative x cube. And similar, we can show that -1 to a third power is just going to stay -1. So this will come out as -x cubed. This isn't f of x. This isn't g of x, but this is negative g of x, because the original function is just x cubed. So if I put a negative in front of it, then that makes it negative g of x. So we were able to show that g of -x gave us negative g of x, and that's the definition of being an odd function. Sure, we can do an example where it's going to be neither odd nor even. So let's do number 40 from the book. So for number 40, we are given a function. It's called h of x. In this case, it's defined as 3x squared plus 5. Right? So we're going to take similar steps. We're going to evaluate h at -x. If we get the same thing, we know it's even. If I get negative h of x, which I can write down what it'll equal to, right? Negative h of x means I have negative of the entire function. Since it has multiple terms, I would need to have parentheses for it. So negative h of x would be that. So if I'll be able to show that my h of -x is this, then it's going to be odd. If it's neither h of x nor negative h of x, then I'll say it's neither. So I'll give you guys like 2 minutes. Go ahead and evaluate this function at -x, and let's see what we get. I just realized that I didn't copy the question correctly. So those of you that are saying this is even, you are correct. This was even, but this wasn't number 40. So number 40 in your book has 3x cubed. So let me change that. This was meant to be 3x cubed plus 5. That's number 40. So go ahead and try it again. So that's going to change your answer probably. All right, so again, with the correction, and I would need to correct this piece as well now, right? Because I changed my function now to x cube. What page is this? So this is, let's see, this is 2-3, and these are from page 82. If you guys are in the book, it's page 82. Number 40 is what we're looking at. So here, if I plug in my input to be negative x, then I would simplify. I would get 3 times negative x cubed plus 5, which would give me negative 3x cubed plus 5. So I see that my first term is positive. I mean negative. My second term is positive. In my original function, both of them are positive terms. If I were to find negative h of x, which I did here on the side, I see that both of them are negative terms. So in this case, it is neither even nor odd because it doesn't equal to the original function and it doesn't equal to the opposite of the original function. So the conclusion is that it's neither. All right, let's have you guys try one more just to make sure that this concept is making sense. How about 38? 38 is not too bad. So here we have f of x is defined as 2x to the 4th minus x squared. So go ahead and check if this is odd or even. I'll give you guys 3 minutes on that. All right, so again, to check algebraically if a function is odd or even, we start by evaluating the function at negative x. In this case, our function is 2x to the 4th minus x squared. Input is negative x, negative x. Here we would get 2 times x to the 4th positive minus x squared positive, because again, from previous page, we saw how this negative, I guess from this page, we saw how negative x squared gives us negative 1 squared, or rather negative 1 to any even power will come out as positive 1. So for that reason, both of these came out as positive terms, but this negative sign, of course, stayed. We just brought it down. So this is exactly the same as the original function, and because it's equal to f of x, that's the definition of being even. So this would be an even function. So even is good. All right. Now let's go ahead and connect this concept of odd and even functions to the graphing of the functions. So last time we discussed function notation, and we said, well, if we have function notation, f of x is equal to the y value. So when we say function value, it's the same as basically the y value at a given input of some x value. But we can use also ordered pair notation, because again, this is just corresponding to the value x comma y. So any ordered pair, the x is the input, the y is the output, can be also read in function notation, where again, x is the input and the function value at x is the output, but that's the same as the y value. So looking back at the odd definition, or let's start with the even definition, we said f of negative x is equal to f of x. So this tells me that for my input, whether it be negative x or positive x, the output is the same. So at negative x, my output is some value f of negative x. When the input is x, my output is some value f of x, but they're equal to each other. So if we switch this over to point notation, ordered pairs, then this is basically saying the following, that for any point x comma y that exists on the graph of function f, if the function is even, there also has to be a point negative x with the same exact value y. Because again, our function at negative x and our function at positive x, they are equal. Their function values are equal. So with this, we get a symmetry. We get a symmetry. So if I draw a little plane, xy plane, then what we're saying is that as long as my function is even, for any x value I choose, there will be some corresponding y value, and there will be this point x comma y. So if there is a point xy, then there also has to be another point negative x, which means opposite of x, but the same exact y value. So both of these points have to be on the graph of my function. Now this defines a symmetry, and this symmetry is through the y-axis. This is my y-axis. And this is my y-axis symmetry, because now if I have any point on the graph, that means I can go to my line of symmetry and then the same distance past my line of symmetry, and there will be another point on the graph for an even function. So let's summarize that. We're going to say that even function is always symmetric, or the graph, I should say, the graph of an even function is always symmetric about the y-axis. Graph of even function is symmetric about the y-axis, as we saw based on the previous discussion. Again, I want you to understand where that property comes from. It comes from that the function values are equal. Therefore, if xy is a point, so is negative xy, and that defines the symmetry about the y-axis for even functions. Now, when we talk about odd functions, that changes things a little bit. So let's do a similar discussion for odd functions. If a function is odd, then we've established algebraically the following relationship. F of negative x is defined as negative is equal to negative f of x. But let's think about what that means in terms of ordered pairs. That tells us that if I have some ordered pair x comma y, then if I plug in negative x as my input, my output is going to be the opposite of y. Because remember, f of x and y, those are basically synonyms depending on what we're talking about. If we're talking about graphs, we're talking about y value. If we're talking about function notation, we just call it f of x. So if I plug in negative x as my input, my output is this negative function value, but that's my negative y. That's the connection that we make from being an odd function. And if we do a graph and sketch those points, regardless of what they are, negative x, it could be negative to begin with, or positive, that won't matter. But just for visual purposes, we're going to put x to be in the first quadrant. So if this is my x and this is my y, and there exists a point xy on my graph of the function f, and so this is my point xy, the symmetry tells me that if I plug in negative x, which means opposite of x, my output is going to be negative y. So there also has to be a point here. It's pretty ugly. Let me clean it up. The point here, which is the opposite of x and the opposite of y. So this also gives me a symmetry, but in this case, the symmetry is not about a line. Instead, the symmetry is about the origin with respect to the origin. So from this point through the origin to this point, these are symmetric. So they're symmetric with respect to the origin. And that's exactly how we define symmetry for odd functions. So we're going to say that graph of odd function is symmetric about the origin. Of course, the origin is the point 0, 0. So it's not symmetric about the x-axis. It's instead symmetric about the origin based on this definition of being odd. So now if we look at a function and then we just look at the graph, we don't need to work through algebra and use algebraic approach. We can just look at the graph and see if there's symmetry and decide from there whether the symmetry gives us odd or even relationship. So let's go ahead and draw a couple of examples. Let's say we have, and I'm just going to sketch them. Let's say we have this parabola for number 1. Let's say we have this graph for number 2. And since we're going to mention these graphs anyway, this is x squared graph. And this guy is cube root of x graph. So would number 1 be odd or even, or neither one of those?
Even?
Yeah, so based on the symmetry, we can conclude that it is even, because any point I choose on the graph, there will be a point opposite to it reflected about our y-axis. So again, if our axis of symmetry is the y-axis, and this is true for all points on the graph, then that gives us even. So this is a graph of an even function, and we already know that x squared is even. We showed it algebraically. Now, what about number 2? Odd or even, or neither?
Odd.
Yeah, so this one seems to be odd because, again, any point I choose, if I reflect it with the respect to the x-axis, it will give me an appropriate point. And because I'm telling you that this is cube root of x, we can also check it algebraically. For example, if I plug in, if my function here, so let's use function notation to make it a little clearer. If my function f of x is defined as cube root of x, we can just plug in a couple of numbers and I can say, well, look, f of -8, for example, would be cube root of -8. That's -2. But f of +8, the opposite, well, that would be cube root of 8. That would be +2. So this gives me a couple of points, right? One of them +8, +2, and the other would be -8, -2. So that satisfies our relationship for being an odd function. From the graph, we can see that reflection, that symmetry, but we could have also showed it algebraically. We could have showed that for any x, not just -8 or +8, but f of -x in general, for cube root of x, no, cube root of -x at this point, we can come out with cube root of -1 to be negative outside, and that would give us negative f of x. So algebraically, we could also show that this is indeed an odd function. And now, but the point here was to also show it graphically. So again, to recap, you have odd, even, or if neither one of those relationships is satisfied, then what we say it's neither. And we can look at odd or even through algebraic approach, through our definition, or through graphing approach through symmetry. So that's that part. The next part, we're going to talk about increasing and decreasing functions. And in general, we know that a function is increasing if we look at it left to right, and it does something like that, it rises. We did that for lines, right? We would talk about lines. This would be a increasing or a positive slope. This would be a decreasing or a negative slope. And if we have a horizontal line, then that's a special case. It's a constant slope. So now we're going to take a similar approach and apply it to general functions. No longer they have to be lines, but the approach will stay the same. If you look at your graph left to right and the y values or the function values are rising, then it's increasing. If you look at the graph left to right and the function values are dropping, then it's said to be decreasing. And if they are not changing, so this is meant to be a horizontal line, then we say that the function values are constant, or the function is constant at that interval. But now we are no longer saying that this has to be a linear function. This could be any function. So instead of drawing a line in between these 2 points, I can instead do this. I can have 2 points, and I have a function that always is increasing. So for any x values I pick, if those x values are less than, so let's do this. So if I pick any x value on this interval, and I pick any other x value on this interval, I call this one x sub 1 and I'll call this one x sub 2, then the corresponding y value for x sub 1, let's call it y sub 1, and the corresponding y value, so this is my first point here, This is my second point here. Y sub 2. So as long as x sub 1 is to the left of x sub 2, or smaller than x sub 2, then the y value corresponding to x sub 1 should be less than the y value corresponding to x sub 2 for any chosen x sub 1 and x sub 2 on that interval. So on that interval, the function is set to be increasing. Now, if we write that in words, then it would look like this. Using function notation, if this is my function f, we could say that on interval I, so on some interval I, again, we're not talking about the entire domain of the function, perhaps just a specific interval. So on that interval I, for any x sub 1 and x sub 2, the following holds true. So on this interval I, if x sub 1 is less than x sub 2, then the function value of x sub 1 should always be less than the function value of x sub 2. That tells me that I will now have an increasing function. And that's what this picture is trying to show you, that as I go left to right, the y values can only increase. They can only get larger. For decreasing, as I go left to right, again, it doesn't have to be a line anymore. If I have 2 points, and as I go left to right, my y values only get smaller, then that's set to be decreasing. The quiz will not be multiple choice, no. Somebody asked in the chat. So for decreasing, again, we can draw this picture and we can explain these, these values. So if I choose any x sub 1 and any x sub 2 on this interval I, then their corresponding y values, this is y sub 1 for this guy, then this will be y sub 2 for this guy. The y values can only get smaller as I go left to right. And to write it as a proper definition, we would say on this interval I, so this was for increasing here, for an increasing function. For a decreasing function, also we're talking about some interval I, for any x values that I choose, x sub 1 and x sub 2, on this interval I, as long as we're looking at it left to right, so that's what this means. X sub 1 is less than x sub 2. It's to the left of x sub 2, so I'm looking left to right. My function values can only get smaller. So f of x sub 1 will be greater than f of x sub 2. So as I look at it left to right, my function values only are falling, decreasing, and that makes the function called or be decreasing on that interval. Again, we're breaking it down by intervals. We're not saying that the function is always increasing or always decreasing on its domain. We're saying that on a given interval it's increasing, or on a given interval it's decreasing. Or it could also be constant. That's the last option. Constant just means that my function values are the same regardless of what x values I choose. the function values don't change, right? So if I choose x value here or here, the function value or the y value didn't change on that interval. So it's the same for any x values on that interval. So let's write in the definition for constant as well. So constant for all x on some interval I, all values of f of x are equal. But again, it's on a specific interval. It doesn't mean that it's constant for the entirety of its domain. So let me try and draw a little graph here, and then I'll give you guys a question from the book. Let's mark some points on this. Let's say I have the following function. And it does something like this. Let's try and make a nice curve. And some arbitrary points. Let's say that this is negative 3, 5. This will be 0, 0. This will be positive 3 and 6. And this will be positive 5, 6. Something like that. So let's say I have this function. It's finite, so it doesn't keep on going. It starts here, it ends over here at this point. If I ask you, what is the interval where this function is increasing? So when we discuss the interval for a function where it's increasing, we only talk about the x values for which the function is increasing. So looking at this graph, I can see that it's rising from, as I look at it left to right, I see that it's rising from this point up until it gets to this point. So on this piece, my function is increasing. Now I have to describe that piece through an interval. And again, when we talk about interval, we talk about x's. We talk about the domain values. So if this is 0.00 and this is 0.36, then on this interval, my function is increasing, and that interval is from 0 to 3. Now, we don't include the 0 or the 3 because at any specific point, it doesn't make sense to talk about function as increasing or decreasing. It only makes sense to talk about an interval as being increasing or decreasing, so the boundary points aren't included. That's the proper way of doing that. So on this interval, we have increasing. Again, note this is not an ordered pair. Not ordered pair, but an interval that we're describing here. Even though the notation looks like I'm saying a 0.03, well, it doesn't make sense to talk about a function increasing at some 0.03, right? So this is not an ordered pair that we're describing. We're simply describing an interval from 0 to 3 for my x values, and my function values are increasing on that interval. If I ask you decreasing, well, I see that my function is decreasing from here until it gets to that point. So on those points, on that interval, it's decreasing. So if I would ask, where's this function decreasing, then you would specify an interval and you would say, well, from -3 to 0, this function is decreasing. And there's also a piece where it's constant. So this piece over here any x value I would choose, my y value would be always the same. It would be 6 on that interval. So this was the interval where my function values were decreasing, and this interval is where my function values are constant, so I would have to describe it as well. So if the question asked you where is it constant, then you would also give an interval, and you would say, well, from 3 until 5, between 3 and 5, my function is constant. Now, you can have multiple intervals where the function is increasing or decreasing or constant. For example, if I would have drawn another piece and I would say, well, from here on, the function does something like that, then I would have another interval where it's increasing, or if it did something else, it could be decreasing, and so forth. So this is an example for us to see how to state the solution. If we have increasing, decreasing, or constant, we state it through intervals, because we're describing an interval as to where that occurs. Let's go ahead and do a question from the book. So let me see if I can find something here that I like. Number 26 will be okay. So I'm going to draw it and give you guys a few minutes to try it. So this is 26. Looks like that, and I'll give you the points. This is -3, 3. This is -1, 0. This is +1, 0. This is 0, 2. And this is 3, 3. And we actually have a few parts to this question. So the first part will be to state all the intercepts. The second part will be to state domain and range. The third part is to do what we were just doing, right? The interval where the function is increasing, decreasing, and constant. So list intervals for each one of those. And for part D, we're also going to state whether it's odd or even or neither. And if you guys have your book in front of you, this is on page 82, number 26. So I'm actually going to project that for you because it's probably easier if you look at it from the book, but then we'll switch back and answer it here. If I can load the book. Let's see if this works. Nope, it logged me out, so I'm gonna have to re-log in. Yeah, it was just working and now it doesn't want to. All right, so I guess I'll just leave you guys with my picture and I'll try to fix my book meanwhile. I'll give you about 5 minutes to work this out. All right, guys. So here I was able to share the book page. Again, if you have your e-text in front of you, probably it's a little easier and nicer looking as opposed to me drawing it. So here's the question. I already drew it. So let me go ahead and go back to my screen. And let's go over these things. So first, the question is to list the intercepts. Again, you have to remember from algebra that intercepts are where the graph crosses the axes. So if you have two-dimensional plane with x and y axis, then we have x-intercepts where the graph crosses the x-axis. So that would be these 2 points. So my x-intercepts here would be -1, 0 and +1, 0. Y-intercept where the graph crosses the y-axis, and we do have a y-intercept here, which occurs at the point 0, 2. So first, again, to mention, when we're listing intercepts, and it's important that you understand, even though I guess the way that we write these things, it kind of looks similar, but it's not talking about the same thing. Here we're talking about ordered pairs, specific points. But when we talk about increasing, decreasing, or sometimes even domain and range, it looks like an ordered pair, but it is not. It is describing an interval. So for our domain is an interval. All the x values where this function is defined. And our function is defined for x values from -3 to +3. At all of those x values, we have a corresponding function value. It doesn't keep going. There's no arrow here, so it's finite. It stops. But there are points included here and here at -3, 3 and at +3, 3. The function exists and is defined at those points. If instead of having a point, we would have had a, let me see if I can erase that. Yeah, so if instead we would have had a marking that looked like this, an open circle, that would tell me my function is not defined at 3, that it has a hole there. And we will encounter examples like that. But on this particular example, this was a closed circle, so it is defined. Therefore, my domain, including -3 and including 3, those are the values, the x values. For my range are the output or the function values or the y values. So those are all the corresponding y values where my function exists, and my function exists between these values, right? That's where my y values exist on the function. If I go below 0, there is no function there. There's no function values there. If I go above 3, like at 4, well, there's no function at 4 up here. So my function is only defined between 0 and 3. And again, 0, it's well defined. I have a specific point, as a matter of fact, a couple of points when my function is 0. And I also have a couple of points where my function value is 3. So those are included in my interval. Now for the increasing, decreasing, and constant, those are the things we were just discussing. So increasing is when my function goes up. So it goes up on this part and on this part, right? Those are the parts where it's going up. As far as my interval, we describe it through the interval of my x values. So from here to here and from here to here, these two pieces, my function is increasing. So increasing. And we do not include the boundary points when we talk about increasing, decreasing. So we're increasing from -1 till 0 for the first part. And then we're also increasing from 1 until 3. Now, these aren't points. This is not an ordered pair -1, 0, and an ordered pair 1, 3. This is an interval as x goes from -1 to 0, and this is a second interval as x goes from 1 to 3. So make sure you guys see that these are not ordered pairs. And when we have multiple intervals, the proper notation is to connect them with a union. So that's where my function is increasing. Decreasing, so I'm decreasing on this region and on this region, right? That's where my function values or my y values are getting smaller as I go left to right. So again, I describe that through my interval on the x-axis. So it'll be this interval and this interval. That's where I'm decreasing. So again, these are not ordered pairs, but instead these are the x values of my intervals. And I go left to right for my intervals. So -3 until I get to -1. I'm decreasing for those x values. And then the second part is from 0 until I get to +1. My function is decreasing at those values. Connect them with the union. There's nowhere that it's constant. If I would have had another piece drawn to it doing something like that to another point, then I would have said it's constant on that region, but there wasn't one, so it's not constant anywhere. So we can say constant and we can put empty set, right? There is no set of values for which it's constant. So on MML, I am not 100% sure what the input is going to be for that homework. Again, you guys will have to see it. I don't remember off the top of my head all the inputs for all the homeworks. If they will simply ask you to put in intervals, then you may not need a union. You may just have to put in few intervals where it's increasing. But hopefully they fixed it where it now uses parentheses, because I know that they were doing it with brackets, then they changed it to brackets or parentheses, but parentheses is the proper way. As far as if it'll need the union in there, you'll have to see on the question how it's asking for you to input it. But you definitely have to put in interval notation. So again, make sure that you guys understand that these are intervals. These are intervals, not ordered pairs. I don't even know if you can see what I wrote here. Here we're listing intervals. Whereas here we were listing ordered pairs. And the notation looks pretty similar, but it means completely different things. Ordered pair is a point on the XY plane. An interval is a one-dimensional interval, in this case for the x-axis. And based on the way that this function looks, we see that there's symmetry here, right? Any point I choose, there's going to be a reflection about the y-axis, and there will be a point opposite to it. So this would be even. This would be an even function. All right, so now we have increasing, decreasing, and constant defined. And before we get to the next part of this lesson, we're actually going to do something. So why is it even? So again, even, we talked about the definition from the graph. If we have reflection around the y-axis, so the y-axis symmetry, then it's even. Yeah, so here we have y-axis symmetry. So we are saying that it is even. All right, so what we're going to do next is I'll project another question, give you guys some time to work on it, and then on top of it a break, because I kind of have to go walk my dog, it looks like. So the next question we're going to work on, 32 seems good. So we're going to do 32, and I'll project it on the board. And let's see, it's 8:06. So with everything, with the time to work on this question and your break included, we're going to start back up at 8:30. So you get around a little more than 20 minutes, I guess, for everything. So let me share 32. Also, it has 4 parts, right? Same parts as before. So follow the previous example and go ahead and figure out this one. And I'll be away from keyboard until about 8:30. right, guys, I am back. Let's see. It's good you guys are talking to each other, comparing answers. I like to see that. All right, so we saw number 32. I'm going to switch over to my whiteboard. And we will go over it. So I'm not going to draw it. I think you guys had time to draw it at this point in your notes, or hopefully you can look in your book, in your ebook, and see the question. So first part is asking us for intercepts, if any. And we do have intercepts, starting with x-intercept. So x-intercepts is our graph crossing the x-axis, and that happens in two places here. One of them is marked as a negative 2.3 with the y-coordinate of 0, and the other is marked as 3 with the y-coordinate of 0. So again, for x-intercepts, it is always the y-coordinate that will equal to 0. For y-intercept, it's vice versa. It's always the x-coordinate that will equal to 0. And in this case, we have 0, 1 as our y-intercept. Part B of this question is asking us to state the domain and the range. Again, this particular example, this is a finite function. It doesn't have arrows extending it in both directions or in either directions. It ends at negative. Well, rather, I guess it starts at negative 3 as the smallest x value, and there is a point at negative 3 for x coordinate, and it ends at positive 3, and there is also a value defined when the input is 3. So both of those are included. That would be our domain. So let's maybe mark it as domain here. Our range are the y values, and we have starting at negative 2 for the smallest y value at negative 2. And the largest y value is 2. So between negative 2 and positive 2, our graph, our function is defined. For part C, that's where we talk about increasing, decreasing, and constant intervals. Let's go ahead and write those down. So it is increasing on the interval between negative 3 and negative 2. That's one piece. It is also increasing on the interval from 0 to 2. And again, when we write this notation down on paper, we would use a union, but on your program it might differ. So you'll have to look into what it wants for that. For decreasing, we have, so decreasing is from 2 to 3 on the interval from 2 to 3. X values, again, remember, these are no longer ordered pairs that we're discussing. These are x values, and it's an interval for x values. So from 2 to 3, the function values are decreasing. And there is a piece where it's constant, and it's constant from negative 2 to 0. So from negative 2 to 0, it will be constant. All right, that was part C, and that should cover the entire domain, right? So that covers the entire domain here. And there is still one more part, whether it's odd, even, or neither. So as we look at it, I can see that it doesn't have any symmetry over the y-axis, because if I were to reflect, for example, 0.22, I should have a point negative 2, positive 2, which I don't, nor does it have any symmetry around the origin. So there is no symmetries that we discussed. Therefore, it is neither odd nor even. So we will just state neither. Any questions on 32 then? before we continue to our not even next lesson. This is a pretty lengthy lesson, but before we continue to the next concept of this lesson. So why is it decreasing from 2 to 3? Let me see if I want to perhaps share the screen again, and it'll be easier to point out. All right, so here's our graph. Let me annotate. So this piece over here is when my y values are getting smaller as I go left to right. That's what we defined as decreasing, right? So on this piece, my y values are decreasing as I go left to right. And that starts to occur at +2. So again, we're only describing the x values where it's happening. And it ends at 3. So this is the interval that we're trying to describe. So from 2 to 3. All right. All right, so let's go ahead and start with our next concept. So let me stop the share here. And the next concept deals with local maximum and minimum, and also the absolute maximum and minimum of a function. So the concept in and of itself of a minimum and a maximum is pretty straightforward. Before I go into any definitions, because the definitions aren't as easy to kind of to decipher when we write them properly, we'll just kind of consider these examples. So let's say I have the following function that does something like that. It goes up, comes down, goes up. And we'll mark some points on this guy. So concept of local maximum or minimum, the definition will include the words that we have to have an open interval. What that means, if we're talking about open interval, is that we have to be able to go further to the left and further to the right on our function in order to have an open interval. So what it really means is that we cannot be on the boundary. So we cannot be on the boundary point. For example, this guy here cannot be a local maximum because I cannot travel past that point. My function ends there. So I cannot create an interval around this point. Therefore, it cannot be local anything. But something like this guy, where I can travel to the left and to the right, right? I can go to the left of this point and to the right of this point. So I can create an open interval around it. Therefore, it can be a local maximum or a minimum. And a local maximum just means that this point has the largest y value on some interval around it. So if I pick some interval around it, again, it has to be an open interval, then this point having the largest y value tells me that it can be a local maximum on that interval. Similar point down here, this guy, because I can create an interval around it, tells me I can be a local minimum because I have the smallest y value in that interval. So this point has the smallest y value, smallest function value on the interval around it. Therefore, it can be a local minimum. So again, local means I have to be able to create an open interval around that point. So this guy, I cannot keep going above, right? I don't have anywhere to go to the right of it. So if my function would have done something like, well, something like that, I guess, then I can discuss it as being local maximum. But since it cuts off there and I have nothing to the right, there's no open interval. Now, absolute, so we're going to have two concepts, local and absolute. Absolute means we're talking about the entire given domain of the function. So local means we're only localizing it, looking at a specific region, like here, that point is the local maximum, but it's not the absolute maximum because I have y values that are above it in this region somewhere, right? The y values are above it in that region, so it's not the absolute maximum of this function. Now, for absolute maximum or minimum, you could be on the boundary point because you don't need to have an open interval. So absolute maximum So for absolute maximum or minimum, you do not need an open interval, so you can be, let's not call it boundary, let's call it like endpoint instead, because boundary, I don't know if I like that word. Endpoint implies you cannot go in one direction from it. So in this case, you cannot go further to the right. In this case, you cannot go further to the left. Whereas absolute minimum or maximum, you can be at an endpoint. That would be fine. But you have to be, to be a maximum, you have to be the largest y value for the entire domain. To be a minimum, you have to be the smallest y value in the entire domain. So for my example here, this guy, this is the highest y value on the entire domain that I provided. It is on a boundary, but that's fine. Nothing wrong with that for being absolute. Local, again, could not be local, but absolute it could be. And this is the absolute maximum of this function because it's the highest y value on the entire function at that point. Now, the absolute minimum of this function happens to coincide with the local minimum. The lowest point for this function occurs here, not just locally, but for the entire domain, right? That has the smallest y value for the entire provided domain. There's no other y values that are below it. So it doesn't have to be on the boundary point. It could be, but it doesn't have to be. It could also be on one of the local maximas or minimas. So this is not only a local minimum, but this is also an absolute minimum.
Can there be multiple local maximums and minimums?
Absolutely, yes. So you can definitely have multiple local max and mins, but you cannot have multiple absolute maximums and minimums. There can be only one basically absolute, but for like if I extended this further and if I did something like this, and then I did something like that, then, well, it looks a little bit wrong. Something like that maybe, or rather it would stop here. Then we would have another local minimum, right? This would be another local minimum. This would not be a local maximum because again, it's an endpoint, and it could not be an absolute maximum because that guy is higher. So there can definitely be multiple local max and mins. So this was a quick sort of overview based on an example. Now we're going to go into a more proper definition of these concepts. So let's go ahead and start with local. So we have local maximum and minimum. That's a fair question, right? If the graph is symmetric, so you could have you can have absolute maximums occurring at different points, but it'll still be the same absolute maximum, right? When we discuss absolute maximum, there's two, or minimum, there's two ways of talking about it: where it occurs and what it is. So where it occurs can have multiple locations, but what it is, it'll be the same value, the same function value, right? So going back to this example, if I extend this further and do something like that, and this point here and this point here have the same y value, then that y value is the absolute maximum, but it occurs at two different locations. So that would be fine, but it cannot be different value. So that's just a little bit of vocabulary that we will introduce here. All right, so starting with local, let's say we have some portion of a graph, and again, this has to be on open interval I. We will call it open interval I. And the word open basically means that we can go to the left and to the right from the point in question. So if it's an endpoint and we cannot go to the left or to the right, then we cannot have an open interval around that point. So we have to be able to, for local. If I have some piece of my function that behaves something like that, then we have a point here, and we're going to say that this x value is c, and the corresponding y value is the function value f evaluated at c, f of c. Then we say that we have a local maximum occurring at c. So local maximum at c if f of c is greater than or equal to f of x for all x's on the interval described here, this open interval I. So whatever is my function value at c, everything else is smaller, or it could be equal to, but usually on the examples we're going to encounter, it'll be smaller. However, it could be equal to as well. So f of c is greater than or equal to f of x for all x's on that interval. So if this is my interval in question, if I choose any x on this interval, the function value at that x should be less than or equal to the function value at c. That makes it a local maximum. And what we say, again, the vocabulary that we use is that it occurs, so local maximum occurs, at c. Its value is f of c, right? So there's two things that are being described. What is the local maximum and where it occurs. So what is the function value. Where it occurs is the x value. Now, for local minimum, it's essentially the same thing, but kind of in reverse, right? So if I have an open interval, it looks something like that. Then if there exists a point but the point has to exist. It cannot be a hole on the function at that point. There has to be an actually defined point there. And again, we're going to call this x value c, and its corresponding y value is f of c. So then this will be considered a local minimum at C if the function value of C is the smallest one. So it's less than or equal to f of x for all other x's on that interval. In the interval I. And again, vocabulary, we describe local minimum or local maximum in two ways, where it occurs and what it is. Or we can also describe it as an ordered pair. Again, if you're doing your homework and it's going to ask to, for a local maximum as an ordered pair, then you would just say, or local minimum, then you would just say, well, it occurs at C and its value is the function value at C, f of C. Like that. So that can also be used to describe a local maximum or local minimum. That way you right away say, well, it occurs at C and it is f of C. So that's our local max, local min. It's an open interval. You have to be able to have an open interval. Let's see, can you have two exact same local maximums? So again, they could be the same value, but you wouldn't be able to have, I mean, if I'm not sure I'm following your question. When you say exactly the same.
What I was trying to say is, like, if C was a whole, like if C didn't exist, to the right of it and to the left of it, wouldn't they both be the absolute mins?
So that is actually a good discussion to have. So if this point has a hole here, right? So we should have a local minimum there, but if our function is not defined at that point, then at least on this interval, there is no local minimum at all, because it should have been where that point is, but we have a hole there. If we have a hole there, then there is no single y value which is the smallest. It would have been at that point, but if that point doesn't exist, then if we go arbitrarily close away from that point, we cannot single out a specific value which is the smallest in that region. It should have been there where the point is, f of c, but if that's not defined, then there is no local minimum in this case.
So we would just say no local minimum?
Yeah. That you can have no local minimum, you can have no local maximum, you can have no absolute minimum or no absolute maximum. All of those are fair results that we can encounter. But to define it, we do need to have an actual point in existence. For example, if a function has an asymptote, like if in this case, I would say this forever keeps going down forever, then I would be forced to say there is no absolute minimum, right? There's still a local minimum, but this absolute minimum would no longer be correct, because I can find infinitely many values that are less than that y value, so it's no longer an absolute minimum if it keeps going down. So in this case, we wouldn't have an absolute minimum, or if the function forever keeps going up to infinity, then we would not have an absolute maximum. So there's different cases to be studied, and that's why some of those examples that you'll encounter in your homework should be pretty interesting to consider. Would it be fair to say the absolute minimum is no? So the way that we define absolute minimum or absolute maximum, it is a value which occurs also at a defined point, and infinity is not a value. Infinity is a concept. So in the future, you'll call these types of functions unbound. But for now, we would just say, well, there is no absolute minimum. We cannot call it infinity because infinity wouldn't qualify in this definition. We can't say infinity is greater than or equal to something, to other infinity. We cannot compare different infinities, basically. So local maximums and minimums, they have to be actual values. They cannot be infinities. Now let's go ahead and discuss absolute max and min, and we'll see that it's a pretty similar definition, but now we get rid of the open interval concept. We no longer care if there's an open interval around that point. As long as that point is defined, we can have absolute max or min there. So absolute maximum and minimum. We have some interval. No longer it says open interval, just says some interval I, and usually it's the domain of the function in question. Usually that'll be that interval I, but it no longer has to be open. So endpoints are now fair game for absolute. And we define in the following way. If there exists some value u, so we're calling it u instead of c now, such that f of u is greater than or equal to f of x for all values of x in this interval I, which again will usually be the domain of the function for us, then f has an absolute maximum there. Then f has an absolute maximum. And again, we describe as to where it occurs. So f has an absolute maximum at u, which is the x value, at x equals u. And f of u is that absolute maximum. So f of u, the function value, is the actual absolute maximum. So if you have 2 points that are, absolute maximums or maximas, that's fine. They occur at different places, but they're still going to be the same value. And for absolute minimum, we just kind of reverse the inequality symbol and we'll say, if there exists v such that, by the way, when you guys start taking calculus and higher division courses, you'll see a lot of nice shortcuts for writing all this out. Like there exists is just that symbol. That means there exists. Math people, we don't like to write a lot, so we have shortcuts for all these things, but I'm not too heavy on shortcuts. We do have a professor that's pretty heavy on those shortcuts. So if you're considering being a math major and you want to get exposed to all these shortcuts and these nice ways of writing properly, proper way of writing all these math sentences, definitely take Chuck Johnson and you'll learn all this nice notation and the whole paragraph becomes like a single line. So if there exists v such that f of v, and now since we're describing absolute minimum, we want this to be the smallest value. So f of v is less than or equal to f of x for all x's. For all would be this guy, I remember some of them still. That's for all x's in this interval I that we're discussing, which again is usually the entire domain. Then f has an absolute minimum, which occurs at this point x equals v, and the value of it is f of v. So those are the definitions for absolute. You can see that they're very similar to definitions of local, but there is a major difference here. The interval I is localized and open, and here it's just some interval I, it's no longer open, and usually it's going to be the entire domain of the function when we're talking about absolute. All right, so now with these definitions, let's try and consider a couple of examples to clear things up. And we'll start with an easier example, number 50. That one I can draw here. Page 83 if you're following along. So we have this. We have a couple of points that are marked. Not necessarily drawn to scale, but that's fine. Like that. So the points that are marked, this is 0, 2. This is 1, 1. This is 4, 4. And this is 5, 0. And the question basically asks us to list absolute and local maximas and minimas. So again, remembering that local cannot be on the boundary, on the endpoint. Let's go ahead and start by listing local max if they exist and local min. And there could be multiple or there could be none. So is there a local maximum in this case?
Yes.
Yeah, there is a local maximum. So 4, 4 would be the local maximum, which occurs at 4, and its value is also 4. Because from this point, we can create an open interval, so we can go in both directions around it. Therefore, it can be local. And since it's the highest point in that local region or local interval, then it's the local maximum. Now, local minimum similarly is 1, 1. Yeah, so this point, we can go around it, so we can have open interval, and it's the lowest point on that interval, 1, 1. Now, absolute max and absolute min. So absolute maximum, 4, 4.
Again, 4, 4.
Yeah. So again, local and absolute, they can be the same one, right? As a matter of fact, there will be a theorem that you guys, if you read the book, you will encounter it, which will tell you that absolute maximum or minimum will always occur either at one of the local ones or at an endpoint. So in this case, my absolute maximum occurs at 4, 4 because that is the highest point for the entire function. What about my absolute minimum?
5, 0.
5, 0.
Yeah, absolute minimum will occur at 5, 0. It's lower than 1, 1. My local minimum was 1, 1. So that minimum is not going to be absolute because there are smaller y values. All of these y values are smaller than 1. And the smallest one happens here at 0. Well, it happens at 5, and it is 0. That's the lowest point for this graph. And it could have an absolute minimum because absolute doesn't require an open interval. That point cannot be a local minimum though. So in this case, absolute minimum is one of the endpoints. 0, 2 would not be a local maximum because there's no open interval around it. It would not be an absolute maximum because there are infinitely many points with a larger y value, with a larger function value. So that would be one example here.
Excuse me?
Yeah, go ahead.
What would happen if 1, 1 was 1, 0?
If 1, 1 was 1, 0, then like, you mean something like that?
Yes.
Then we would have had a local minimum at 1, 0, and we would have had absolute minimum occurring at 2 points, one of them at 1, 0, and the other at 5, 0. But 0 would still be the absolute minimum.
Okay.
Now let's consider a more interesting example, and we'll probably do 2 more on these, and then we have to move forward. So something like 52. That one is a little trickier. There's some holes in this graph. So there's a point here. There's a point here.
Sorry to interrupt,
Yeah.
but I believe, didn't you say earlier that you can only have one absolute minimum and one absolute maximum, and you can have multiple local minimums and maximums?
So we have to be careful with the language that we use if we say that. So we can have absolute maximum occurring at different locations.
Okay,
So
but I see.
But
So
the
it's a way to say
value,
it.
yeah, but the value of it will still be the same, right? So the absolute minimum would have still been 0 given that previous discussion, but it would be occurring at 2 different locations.
Got it. Okay, I got a little confused by the phrasing. Thank you.
Yeah, it's just not. It's basically just phrasing of it is exactly correct. So let's say we have the following piece of our graph here. Mark some points. This will be 0, 1, but notice that some of them are points where some of them are holes. This is 1, 3. This is 2, 4, and this is 3, 2. And it's the same question list, any and all local maximas, local minimas, and then absolute maximums and absolute minimums if they exist. So I'll give you guys about 3 minutes or so to think on this one. Write down what you think are the correct values, and then we'll go over it. Again, keep in mind that there are some holes in there, which means that the function is not defined on that point. All right, so again, this one is a little trickier because of those holes in various places where we would expect to have some local maximums and local minimums. Can a local max and min be at the same point? No. So the local maximum and the local minimum cannot occur at the same point. No, that wouldn't be possible. So in this case, local maximum, right? So where we would have a local maximum would be here, right? If one were to happen, because at that point we can create an open interval around it. But the issue is there is no point there. So there is no point at 2, 4 where I should have a local maximum. And because there's a hole there, then we would just say none. So there is no local maximum. Actually, I take that back. A local maximum and a local minimum could occur if you have at the same point, if you have a constant function, then well, actually, no, I'd need to think a little bit like those special cases. So for now, I'm just going to say no. In the regular case, you can't really have a local maximum and a local minimum occurring at the same point.
Professor?
Yeah.
Now, would 1, 3 be a local maximum, or is that not possible?
That would not be a local maximum, because if I create an interval around this guy, well, as soon as I go a little bit to the right of it, I already have higher y values than 3.
I see. I got you.
Right. So it has to be the peak. It has to be, the peak on that region. So 2, 4, if this had a point here, that would be the peak of that region, because if I go to the left, I'm lower. If I go to the right, I'm lower. But the issue is there is no point at 2, 4. The function is not defined there. That's why there isn't a local max. And there's no other options for a local max because, well, there's no other humps, basically, right? And local maximum or minimum can only occur at where we have those humps. And local minimum is a similar, well, not a similar discussion, but it's also none, right? There is not a single point around which I can create an open interval, right? This would have been a good candidate if the function would have kept going. Then I would have a local minimum there. But because it doesn't keep going, it's an endpoint, I cannot have a local minimum there. Similar, yeah, go ahead.
Can we say that 1, 3 can be the minimum value, local minimum?
No, 1, 3 cannot be local minimum or local maximum, because as I go to the left of it, my function values are decreasing, so it's not a minimum. If I go to the right of it, my function values are increasing, so it's not a maximum. So 1, 3 is neither.
No, I mean the local minimum.
So again,
it's increasing. Okay, I got it.
Yeah, if I can find smaller values, so no matter how small of an interval I create around this point, as soon as I go a little bit to the left, I already have a smaller y value. So it's not a local minimum. As soon as I go a little bit to the right, I have a bigger y value, so it's not a local maximum.
It has to be exactly the lower point.
Say that again?
So it has to be the lowest point.
Correct. It has to be a local minimum, has to be the lowest, smallest point on that interval, yeah.
Thank you.
So for local minimum, also there are no candidates here. 3, 2 cannot be local minimum, first of all, because it's a hole, but second of all, also because there's no open interval around it. Now, when we get to absolute, there is rather, one of them. So which one exists? The absolute max or the absolute min? So the absolute min is here at 0, 1, right? That could be an absolute minimum or maximum. Well, I shouldn't say minimum or maximum. I should say that endpoints can be absolute minimums or maximums. But in this case, the point here is defined. There is a point here. There's not a hole there. And we don't need an open interval around it. And it's the lowest point, right? There are no other points on this function that have a smaller y value. So that would be an absolute minimum. If I look for an absolute maximum, there isn't one, because again, the highest point where it should be has a hole in there. So 2, 4 has a hole on it. It's not defined. And as soon as I go a little bit to the left or a little bit to the right, that concept of arbitrary, arbitrary smaller, we cannot sort of pick out a point that's above all the other ones. I can always say, well, I can go a little bit more, like 3.999 or 3.9999, so I can get arbitrarily close to 4, but at 4, I have a hole. Well, at 2, I have a hole, rather. So as I get closer and closer to 2, my values keep increasing, but there's no one value that we can say that's the largest one. It should have been at 4, but there's a hole there. All right, so that's a nice example. Let's also consider another one and see if, let me pick which one I like here. I think, yeah, we'll do 54 to throw an asymptote into the mix. So let me sketch a graph of what we have going on here. We have a point, another point, another point. And the function keeps on going down. So the points here are -1, 3, 0, 2, and 2, 4. Same thing. So I'll give you guys like 3 minutes. List the local min, local max, then the absolute min, and the absolute max. So go ahead and take 3 minutes, think about it, write them down if there are any. All right, so you guys had some time to think about it, and I see a few correct responses there. So when we talk about local, again, this only is local to a specific interval. It doesn't have to be an entire domain, and it also has to be an open interval. So the lowest point, if I consider, for example, this open interval here, then the lowest point is going to be 0, 2. So that is a local minimum. It satisfies all the needed requirements. I have an open interval around it, and it has the smallest y value, the smallest function value on that interval around it. Now, local maximum, only this guy satisfies the local maximum requirement. So there's a local maximum at 2, 4, because again, I can create an open interval around it, and it's the largest y value, the largest function value on that interval. Therefore, it's the local maximum. This guy cannot be a local maximum because there's no open interval around it. So -1, 3 is neither. It's nothing. It's not a local nor it's an absolute, because, well, 4 is the largest value, right? So 2, 4 would be an absolute maximum, because 4 is the largest value for the entire domain. There are no y values greater than 4. So 2, 4 is also the absolute max. Now, absolute min, there isn't one, because my function keeps on going and going and going to -infinity. So there's no single value where we can say this is where the function is at its lowest point. So that would be our final answer here. So again, some of these, there's a few more examples we could do, but we are limited on time. We have to move on forward. So I will ask that for questions dealing with things like average rate of change and the secant line, that you guys will have to consult the book to look at the examples dealing with. So let me write it on the next page, actually. So on your homework, if you encounter problems with average rate of change or the secant line, you will have to consult the book or videos or any other resources that you prefer. And we have to move on to our next lesson, which is 2-4, because we only have about 30 minutes left. A little bit less because I'll have to do a roll call. But 2-4 is a much shorter lesson. 2-4 talks about library of functions. And also something called a piecewise function. So first we'll discuss the library of different functions that we will be dealing with. Most of them are review, and I'm not going to graph each and every one of them and spell out all their details, but most of them are covered in algebra. So if you need to review them, you can always review them again, either in the glossary or in your algebra books. But functions like f of x equals x squared, the quadratic function, we know that the general shape of a quadratic function is a parabola. It should be a little more symmetric. Now that we've learned different properties, we can also talk about things like, is it increasing, is it decreasing, talk about its domain, talk about local and absolute maximums and minimums, talk about what else? Yeah, I think that's pretty much it. So for example, if this is f of x equals x squared, I can now ask you, well, what is the local minimum here? And well, we should say that the local minimum would be at the origin 0, 0, or the vertex 0, 0, as well as the absolute minimum would be at 0, 0. And if I ask you about absolute or local maximums, then we would say there aren't any, because it keeps on going forever to infinity. And if I talk about where is it increasing, you could say, well, it's increasing from 0 to infinity. It's decreasing from negative infinity to 0, things like that. But those are, again, functions that we've dealt with before. And if we know the graph, then we should be able to discuss the newer concepts for them. I can also ask you if it's odd or even or neither. So that one would be even. F of x equals x cubed. We know that in general, these functions look like that. And we could get their graphs by just plotting some points if we ever forget what they look like. So this would be an x cubed function. Again, we can talk about maximas and minimas, and this guy has no local or absolute maximas and minimas, because it forever keeps going to infinity and there's no localized region where I can select a point to be a local max or min. Also, let's throw in the absolute value function. If we were to graph absolute value functions, we would be getting these V shapes. And that's how absolute value function looks like. It's basically two lines. As a matter of fact, it's exactly two lines. And when we talk about piecewise functions, we will mention that. Now, the domain for all three of these that we have listed, the domain is all real numbers. I can plug in any x value, whether it be positive or negative or 0. So the domain would be all real numbers on these. But there are functions that we dealt with that have a limited domain. For example, the square root function, f of x equals square root of x. The graph of that would look like this. Right, so this does have an absolute minimum at 0, 0. Doesn't have an absolute or a local maximum, doesn't have a local maximum. And it doesn't have a local minimum as well, because it's a boundary point, right? So we wouldn't be able to create an open interval around it. Also, the domain here would not be all real numbers. The domain would be only the non-negative values. So the domain would be x's that are greater than or equal to 0. So things like that we have to be able to discuss with these. Cube root of x, that also is something that can come up. If we plot some points, we would be able to get a graph for the cube root function, and it would look something like that. Right, that's the cube root function. The domain is, again, all real numbers here. Later on, we will also deal quite a bit with rational functions. So parent function for rational 1 over x. This we will discuss in a lot more detail later, but for now, if we were to graph it, it's a couple of portions to it. It looks like that. So those we will deal with quite a bit for rational function sections. We will do graphing. We will do a bunch of properties, asymptotes, all that good stuff. But in general, if we plot some points, that's what the graph would look like for 1 over x. All right, now what we want to do, the new part here, is to talk a little bit about piecewise functions. Piecewise functions. And piecewise functions are functions that are defined by different expressions on different parts of the domain. So the definition would be essentially different functions for different parts of domain. And we'll do two quick examples just to make sure you guys understand what I'm talking about here. One is, we will make it up. We will say we have an x square function, f of x equals x squared, but only for x's that are strictly less than 0. So this bracket denotes that we're talking about a piecewise function, and then we list the different pieces, the different functions, and we specify on which domain they occur. We're going to say f of x equals 3 when x is 0, and we're going to say f of x equals the square root of x when x's are strictly greater than 0. So this would be a piecewise function. It has 3 pieces, right? 3 different functions are used here on different parts of the domain. Is different function. So if I ask you to graph it, you would need to remember, well, how do I graph x squared? How do I graph just f of x equals 3, but keeping track that it's only at x equals 0. So the graph of this, without doing, too much of scaling, we will do a little bit. The x squared function, I know it's a parabola, and I know it has some points like 1, 1, 2, 4, 0, 0, but at 0, this piece is not defined because it says x is strictly less than 0. So I would have a hole at 0, and then only x's that are less than 0, that's where this x squared is defined. So only the left side of the parabola would be graphed, and there would be a hole at the origin, at the vertex. Because at 0, I would have a specific point for my function. At 0, my function takes on the value of 3. So when x is 0, the y value is 3, or the function value is 3. And the last piece is for all x's that are strictly greater than 0, and my function is defined as the square root of x. And I also know I have some points. Square root of 1 is 1, square root of 4 is 2, and it would keep going. Square root of 0 is 0, but this would again have a hole here. This wouldn't have a point because it's strictly greater than 0, and 0 is not included. So that piece would be the last piece of this function. Now, if I ask you for the domain of the entire function f, well, the domain for this whole piecewise function would be the union of all of the pieces that it contains. But the pieces are everything less than 0, 0, and everything greater than 0. That includes all real numbers. So the domain of this guy would have been all real numbers for the entire function f. If I ask you to evaluate it at certain points, then you have to be careful. For example, if I ask you to evaluate f at a -2, you have to first say, well, where is this -2? Where does it fall on my pieces, right? -2 would fall at this piece because -2 is less than 0. So the function I would be using would be x squared function, and I would plug in -2 in there. -2 squared is 4. If I ask you to evaluate f of 0, well, that would be 3. If I ask you to evaluate f of 9, for example, 9 is greater than 0, so that would fall in this portion. So that tells me I should be using the square root function for that input. and square root of 9. So the value here would be 3. So again, depending on where your input is, you have to use the proper corresponding function for that input. Now, the last example is actually something that we already know, absolute value. So we know this guy, f of x, is equal to absolute value of x. But the actual definition of absolute value is actually a piecewise function. F of x, which is equal to absolute value of x, is actually defined as a piecewise function. So if we don't use the definition of the distance from the point to 0 on the number line and so forth, we can use the piecewise definition. So f of x is equal to x when x's are greater than or equal to 0. F of x is equal to negative x when x's are less than 0. That is actually how we can define the absolute value. Because now if I ask you, well, what is f of negative 3, for example, which we know means absolute value of negative 3, we know it's 3, but here we can see through this piecewise definition that negative 3 is over in this part of the domain. X is less than 0. So the function that we would use would be negative x. The input is negative 3 minus negative 3 gives us 3, as we would expect. If we look for f of 2, for example, well, absolute value of 2 is in this part of the domain. It's greater than or equal to 0. So the function is defined as just x. So it would just be 2. So all the values would match up. But with this definition, if you now think back to solving absolute value equations or solving absolute value inequalities in algebra, you remember how we would always split it up into two cases. That's exactly why we split it up into two cases, because it's defined as a piecewise function with positive and negative options domain. So we would consider both of those options when we would split it up. So there's now a good explanation why we were splitting it up and having two equations to solve when we were setting up absolute value equations or inequalities. All right, so you'll have a couple of piecewise functions again that you'll have to consider for your homework. Now, I am going to start on the roll call, so let me set up for that. And then we'll have maybe 5 or so minutes, 10 or so minutes to address some questions in the end. And the quiz should open up around midnight today and will be due midnight tomorrow. All right, so I'm going to go with your first names. Today's Tuesday, September 8th. Okay, so if you are here, make sure you guys respond here through your microphone, unmuting yourself, or type here in the chat. I prefer microphone option. Kenya. Thank you. Amr.
Here.
Amanda.
Here.
Colin.
Here.
Alexander. Alexander Boychenko.
Here.
Thank you. Olivia.
Here.
Gevorg Galijan. Thank you. And Gevorg Galibian. Thank you. Aranza. Thank you. Joseph. Joseph Gonzalez. No, oh, Joseph is here. Got you. Lindsay. Annie. Ani. Ani Grigorian. No Ani. Chloe.
Here.
MD.
Here, Professor.
Thank you. Vartkes. Vartkes Hovsepian. No Vartkas. Susan?
Here.
Roman?
Here.
Jennifer?
Here.
Gurgen?
Here.
Oscar? Oscar Moscoso?
Here. Sorry about that.
Oh, thank you. Adam?
Here.
Anastasia?
Here.
Oganes? Oganes? John. Okay, gotcha. Serene? Thank you. Anna? Anna P.
Here.
And Anna R.
Here.
Thank you. Maria?
Here.
Alan? Russ?
Here.
Test,
Here,
test.
Professor. I'm here.
Thank you. Andres?
Here.
America?
Here.
Susie?
Here.
Suzanne? Thank you. Michael? Thank you. Nagera?
Here.
Natalie?
Present.
Renee? Renee Ventura? Oh, thank you. Got you. Darlene?
Here.
Adriana?
Here.
Alan?